Hello and welcome to advanced lectures on Kubernetes. What I intend to do is go a bit deeper into Kubernetes. It's a bit more than what architecture certification exam requires, but as an architect, it's really good to know Kubernetes in greater detail. So I'll be talking through the history of Kubernetes, why Kubernetes was born, then we will look at the open source Kubernetes architecture. Then we will look at the managed version from GCP. Then when it comes to Kubernetes, networking plays a very important role. So we'll be looking at GKE networking part, and then we'll take a look at an example of how the deployment is done. So with that, let's get started. But in terms of the history, you know, we used to have a traditional deployment sort of era where organizations will run applications on physical servers, and physical servers were hardware operating system, and then you have multiple apps deployed on it. There was no way to define resource boundaries for applications in a physical server, and this caused resource allocation issues. And all of us have gone through that. Then the industry evolved into uh, using hypervisors, which let you divide the physical servers into multiple virtual machines, and it which allowed you to run multiple VMs on a single physical server CPU. So virtualization allowed applications to be isolated between virtual machines. Each of the virtual machine had a copy of operating system libraries and their set of applications. And but it's still the you know there was definitely the benefit of resource allocation and also security, because applications running on one virtual machine cannot access applications running on another virtual machine. But it was still constrained in terms of the communication between apps and better utilization of the uh, underlying operating system. Then the industry evolved into using a concept called containerization. And also with the advent and adoption of microservices architecture, it became a sort of more and more trusted way of deploying application. So as a containerized application, you had the hardware operating system, and then a container runtime was introduced, which let you run your applications in different containers. So each one of the container had a bin and library and an application on top of it. And all of these containers use the container runtime to run their application on that physical server. So let's look at why containers. Uh, the agile application creation and deployment. So in the last 5 to 10 years, business agility to be able to deploy things faster gained a lot of momentum. And that came with innovative ways of deploying applications. Of course, microservices architecture was one of the key drivers, but it's also how we started looking at applications. Loosely coupled, distributed, elastic, liberated microservices. Applications are broken into smaller independent pieces and can be deployed and managed dynamically, not a monolithic stack running on one big single purpose machine. In the traditional era, we used to have this big, heavy monolithic application that will be deployed, and accordingly we will scale it. But that sort of changed with the loosely coupled applications, and then most of the retail, all of the sort of a web traffic and all of that moved towards the microservices architecture. Then the CI/CD, continuous development, integration, and deployment played a very big role, because from a waterfall model we moved towards agile-based or sprint-based model. We needed to showcase the application in its sort of like a sorter sprinted timelines, and that fostered a cultural change in the industry to look at continuous deployment process. and microservices architecture was a de facto uh, player in making that possible. Environmental consistency across deployment, testing, productions runs the same on laptop as it does in the cloud because it was all mandated by the container runtime and the way you create a container. So whatever you build on your laptop runs exactly same on any environment. Cloud and OS distribution portability, same as that. It doesn't matter which operating system because in a traditional era, all of the libraries, all of the runtime were highly, coupled with the underlying infrastructure, underlying operating system. It sort of made it really difficult to port the applications. Then application-centric management raises the level of abstraction from running an OS on virtual hardware to running an application on an OS using logical resource utilization, high efficiency, and density, because it made everybody realize the amount of resource that is actually required for a container rather than in a monolithic stack where only the runtime can actually tell you, how much memory or CPU it's actually consuming. So then the idea about, because there were so many containers and containers were doing the job, there were lots and lots of containers started being spun up. So there was a need for a process to actually manage the life cycle of containers. And that's where Kubernetes was born. Um, what it let users do, service discovery and load balancing. So Kubernetes can expose a container using the DNS name or using their own IP address. If traffic to a container is high, Kubernetes is able to load balance and distribute the network traffic so that the deployment is stable. So again, it all came down to container is useful, but to be able to manage lots and lots of containers in any deployment sort of became you know the the next major requirement. Storage orchestration, which is Kubernetes allows you to automatically mount a storage system of your choice, such as local storage, public cloud providers, and more, automated rollouts and rollbacks, automated bin packing. So you provide Kubernetes with a cluster of nodes that it can use to run containerized tasks, and you tell Kubernetes how much CPU and memory each container needs. Kubernetes can fit containers onto your nodes to make the best use of your resources. Then the self-healing, Kubernetes restarts containers that fail, and then the secret and configuration management. So, and we'll be looking at Kubernetes much more in detail, but the idea of this slide is there was a need to move towards the loosely coupled microservices architecture, and that was provided by containers. But with the abundance of containers, there was a sort of a controller was required in terms of making sure the Kubernetes run properly, making sure they are routed properly, making sure they are load balanced properly, making sure that they are healed automatically, making sure that the secrets and the configuration management across all of these containers are managed properly. And that's where all of that combined together, Kubernetes was born. And Kubernetes was actually born out of Google, and then Google made it an open source tool. If you want to learn more about Kubernetes, I would recommend these two playgrounds. They give you uh, pre-existing clusters, or they spin up clusters with two nodes, or sometimes with one node, where you can try all of the Kubernetes commands to to run it without having to set up your cluster. Katacoda is I've personally used it before. It's really helpful. And then you can use the another one is play with Kubernetes. And let's look at the open source Kubernetes architecture. Kubernetes, it's a portable, extensible open source platform for managing containerized workloads and services that facilitates both declarative configuration and automation. This is very important to understand for Kubernetes because all of the deployments are declarative. A Kubernetes cluster consists of a set of worker machines called nodes that run containerized applications. The worker nodes host the pods that are components of the application workload. The control plane manages the worker nodes and the pods in the cluster. So let's look at this diagram, but let's look at it in sort of three panes. The one is these nodes. So think of these nodes as virtual machines. And then you have these pods, and that's where those applications are run. So you have pods within a node, and you can have multiple nodes. And then you need a way sort of to manage everything that runs on these nodes or these pods. And that component is called control plane. And then I will go through each and every component, but just that's the way to view the whole Kubernetes architecture is the smallest deployable sort of unit within a Kubernetes cluster is a pod, which is this particular part of it. So this is a pod. Now, when the applications are deployed, they are deployed inside a pod. So you can have multiple pods under one node, and you can have multiple nodes inside one cluster. And the body, this combination of tools that manages this set of pool of nodes and the applications running inside it is called control plane. Now, let's go through each one of these components. So if we first look at the control plane, now the front of the control plane is the API server. It's the what it gives you the front end and the inter-cluster communicator. So any application or anybody who needs to interact with the Kubernetes cluster needs to come through API. API server. It exposes an HTTP API that lets end user communicate with the cluster. And at the same time, it is also used by other components which are used for the inter-cluster communications. Then the next one, and I will follow this path, is the Cloud Controller Manager. So Cloud Controller Manager, it's part of control plane that embeds cloud-specific control logic. So nodes, routes, service controllers. Because Kubernetes can be deployed on any cloud, it's an open service architecture. So this particular component helps with adopting any specific cloud. So whether it's Google, Azure, or AWS. Then you have Controller Manager. So Controller Manager, it abstracts components to reduce complexity. So node, replicas, endpoints, service accounts, token controllers, and all of that. Then you have etcd. etcd, it's a distributed key value store used to store state information. So all the information about the cluster is stored in this key value store. And then you have scheduler. So scheduler is it's a low level compute abstraction to run pods. So if you look at this entire control plane, you have you have one endpoint from where you go and interact everybody. So sort of call it a traffic router, the front end, and then you have a control manager for the cloud. You have the control manager to control and manage nodes, routes, and everything. Then you have a store to actually store the state about the cluster, and then you have the scheduler, which is low-level abstractions to actually run jobs and everything. Now, when you come towards the cluster side, if you remember, these individual ones are pods. Containers run on pods. One or more pods are part of a node. And the combination, and you can have multiple nodes, and all of these nodes are part of a node pool. So when you come to a node, node components run on every node. So and they maintain running pods and providing the Kubernetes runtime environment. There are two primary ones, kubelet and kubeproxy. So you can see the kubelet and the kubeproxy. Kubelet, it runs on every node to make sure that the container is running. Kubeproxy, a network proxy to maintain network rules on pods. So apart from all of these sort of high-level architecture components, it provides several built-in workload resources, because everything that we talked about it's more to do with how the architecture in terms of components is established. But apart from that, there are a lot of requirements for workloads. Workload is defined in terms of the actual application request, or actual domain business that's being run on this cluster. So some of them are deployment and replica set. Deployment is a good fit for managing a stateless application workload on the cluster. Stateful set. Stateful set is if your workload records data persistently, you can run a stateful set that matches each pod with a persistent volume. So to give an example, if you are running a web application which is stateful, that means it needs to interact with the database to store some information. You can use a stateful set, and as part of the stateful set, whichever pods are part of it, they will all share the same persistent volume. Daemon set. It defines pods that provide node local facilities. These might be fundamental to the operations of the cluster, such as networking helper tool, or be part of an add-on. So that basically gives you access to pods, to the internals. So anything you need to do at a very low level, or sort of machine level or node level inquiries, and a lot of the monitoring tools are used for that. Then job and cron job. They define tasks that run to completion and then stop. So you also get an option to run cron jobs, or sort of a job. So it's not just meant for only the deployable microservices application, but you can also run job and cron jobs. Now let's look at the Google managed version of it. So everything that you saw before is the open source Kubernetes architecture. What Google Kubernetes Engine provides is a managed environment for Kubernetes using Google's infrastructure. Kubernetes draws on the same design principle that run popular Google services and provides the same benefits. So automatic management, monitoring, and liveness probes for application containers, automatic scaling, rolling updates, and more. GKE cluster control planes are automatically upgraded to run new versions of Kubernetes as those versions become stable to take advantage of newer features from the open source Kubernetes project. And why this is important is if you look at any of the managed services of any open source products, there's always a lag between the latest capability versus what's supported. But GKE is pretty aligned to the stable versions of Kubernetes. So the moment it becomes available, it automatically it's upgraded. So if you look at this particular part of it, exactly same concept. Nodes where you have pods run containers. There are multiple pods within the same node, and there are multiple nodes which are part of the cluster. In terms of the cluster, API server, which is the front end, which exposes APIs to communicate with the cluster. You have resource controllers, you have a scheduler, and you have storage. Users can connect through kubectl, and we'll talk about this in detail. And it's everything that Google has in terms of networking, load balancing, operations, all of that is by default uh, available with native integration to the entire cluster. So in terms of VPC networking, persistent disk, load balancer, and the cloud operations. So if I have to summarize it, you, you understand the benefits of Kubernetes. Now, what Kubernetes on Google Cloud provides you is it's some of these benefits. The Google Cloud's load balancing for compute engine instance, node pool to designate subset of nodes within a cluster for additional flexibility, automatic scaling of clusters node instance count, automatic upgrades for clusters node software, node auto repair to maintain node health and availability, logging and monitoring with Google Cloud's Operations Suite for visibility into your cluster. Now, when it comes to the operation of it, not just being a managed services, Google provides two options, and this was recently introduced about a week ago. Is there are two modes of operations that Google provides: autopilot and standard. Standard is the standard way of sort of setting up the cluster, giving you all the flexibility, but you actually manage your nodes and how they all interact with each other. Google has introduced autopilot, which is it manages the entire cluster and node infrastructure for you. So it provides a hands-off Kubernetes experience so that you focus on your workloads and only pay for resources required to run your application. Autopilot clusters are pre-configured with an optimized cluster configuration that is ready for production workload. Now, autopilot is supposed to be a game changer because there's a lot of effort that goes into maintaining Kubernetes clusters. It's in terms of understanding your workload, in terms of understanding how many pods you need, how to distribute your nodes, what sort of configuration you need in terms of CPU and RAM, and then how you will connect it to load balancers and all that. There's a lot of administrative tasks that is required. Google intends to automate that entire process and get you completely hands off, that you just put a workload and it will automatically provision everything. So sort of it's moving towards a BigQuery kind of you know analogous frame, is where you just submit your query, and it will take care of all of the underlying infrastructure. Now let's look at some of the cluster configuration artifacts that you need to know. So apart from the Kubernetes components, there are some of the cluster configuration which is very handy. One of them we talked about node pools. A node pool, which is a group of nodes within a cluster that all have the same configuration. Node pools use a node config specification. Each node in the pool has a Kubernetes node label. So something like this, cloud.google.com GKE node pool, which has the node pool's name as its value. So it's like templatizing, and if you remember uh, the instance template of VMs, so think about it from the same point of view. Node images. When you create a GKE cluster or node pool, you can choose the operating system image that runs on each node. GKE Autopilot cluster only uses the cause contained node images. So you can look at these are the three images that's available with Kubernetes. The container optimized OS, one with contained, and another one is with Docker. Then the Ubuntu image, again with contained and Docker, and the Windows servers. So it's very important to understand that you can actually run a Windows server on as a node image. Now, uh, it's so the container optimized OS is from a Google node image, are based on a recent version of Linux kernel and are optimized to enhance node security. container optimized US images are backed by a team at Google that can quickly patch images for security and iterate on features. And this is also the default one. And it provides better support security and stability than other images because it's optimized for container application. Then the cluster autoscaler. GKE cluster autoscaler automatically resizes the number of nodes in a given node pool based on the demands of workloads. You don't need to manually add or remove nodes or over provision your pools. Instead, you specify a minimum and maximum size for node pools, and the rest is automatic. So it's if you remember the node pool, so all of the nodes, they're the most important constituent part of the cluster. So and the deployment happens based on the declarative language, and we will look at those YAML files. So all you need to do is provide a minimum and maximum size for the node pool. If pods are unschedulable, because there are not enough nodes in the node pool, cluster autoscaler adds nodes up to maximum size of the node pool. And if the nodes are underutilized and all pods could be scheduled even with fewer nodes in the node pool, cluster autoscale removes nodes down to the minimum size of the node pool. If the node cannot be drained gracefully after a timeout period, which is 10 minutes right now, the node is forcibly terminated. And this grace period is not configurable for GKE cluster. Then you have horizontal pod autoscaling. HPA changes the shape of your Kubernetes workload by automatically increasing or decreasing the number of pods in response to the workload, CPU, or memory consumption, or in response to custom matrix. Vertical pod autoscaling, it frees you from having to think about what values to specify for a container CPU request and limits and memory request and limits. The autoscaler can recommend values for CPU and memory request and limits, or it can automatically update the values. So if you look at the Kubernetes architecture, apart from the control plane, which is mostly managed, it all of the heavy workload is on the nodes, node pool, pods, and the containers. Container is where your business logic is. So Google is moving towards it provides a lot of flexibility in terms of all you need to care about is your workload, what application you want to deploy on a container, how that container is managed within a pod, how much scaling is required for that pod, whether it's horizontal or vertical. Then you go one level above is the nodes, how many nodes you need, how it is managed from the node pool. All of that, Google takes care of. Now let's look at some of the networking concept. And when it comes to Kubernetes, networking plays a very, very significant role. Let's look at some of the concepts and then we will see how the networking actually happens. So some of the networking concepts is the whole networking model for Kubernetes relies heavily on IP addresses. Services, pods, containers, and nodes communicate using IP addresses and ports. Kubernetes provides different types of load balancing to direct traffic to current pods. So there are primarily like three kinds of IPs, right? The IP address assigned to a service. In other documents, it may be called the cluster IP. This address is stable for the lifetime of the service. Then you have pod ID, the IP address assigned to a given pod, which is ephemeral because the containers are deployed, containers run within a pod. And when pod goes down, it's basically that IP is released. Then you have a node IP, the IP address assigned to a given node. So let me clarify a little bit in terms of what does this service mean, which is in Kubernetes, you can assign arbitrary key value pairs called labels to any Kubernetes resource. So any of the Kubernetes resource, you have a key value pair, Kubernetes uses labels to group multiple related pods into a logical unit called a service. A service has a stable IP address and pods and provides load balancing among the set of pods where labels match all the labels you define in the label selector when you create the service. So to put it really simple, think of a service from a business use case. So for a business case, let's say it's a retail shopping. Now for that you have a lot of different containers. One does the payment, um, one does the bucketing, one does the cart kind of thing, and then all of these are combined into one service. So that service IP and the way it is grouped together is based on the labels that is provided to each one of these. And when you select based on these labels, so you can uh, group all of these pods which are running services or which are running your business logic for this particular business use case, which it's a uh, it's a term to combine and co-locate them and to be able to trace them. That's the concept of services within Kubernetes cluster. So you have a IP for that particular service. The reason it's called cluster IP because you could potentially have none of these sort of virtual separation of services, but rather everything could be running on the cluster and you provide one cluster IP. IP allocation. Kubernetes uses various IP ranges to assign IP addresses to nodes, pods, and services. Very important to just keep in mind every time you are interacting with the Kubernetes cluster, there is an IP for the cluster, which is from a service point of view service. There's an IP for the node, there's an IP for the pod, and there are various IP ranges that it. First thing first, each node has an IP address assigned from the cluster's virtual private cloud network. So it's well integrated with VPC networks. Each node has a pool of IP addresses that GKE assigns pods running on that node. So CIDR block by default. Each pod has a single IP address assigned from the pod CIDR range of its nodes. So this IP address is shared by all containers running within the pod and connects them to other pods running in the cluster. I hope it's keep becoming more, it's clearer, is that so you have a CIDR block for the node, and then you have a CIDR block for the pods. Now each pod has one single IP address, so all of the containers that's running as part of the pod share the same IP address. And that's what enables them to connect them to other pods running in the cluster. Each service has an IP address called the cluster IP assigned from the cluster's VPC network. Now, this was more about the IP allocation. Then kubeproxy, it manages connectivity among pods and services using the kubeproxy component. So you had the sort of IP allocation for each one of these nodes, pods, and services. Then there's the kubeproxy component is what is used to manage connectivity between pods and services. And this is deployed as a static pod on each node by default. Kubeproxy, which is not an inline proxy, but an egress-based load balancing controller, watches the Kubernetes API server and continually maps the custom cluster IP to healthy pods by adding and removing destination NAT rules to nodes IP table subsystems. When a container running in a pod sends traffic to a service's cluster IP, the node selects a pod at random and routes the traffic to that pod. So the combination of having IPs defined to cluster pod and node and the kubeproxy makes the communication between between containers, pods, nodes, and cluster possible. Now, this was all about what happens inside. And i- if you don't want to get into a lot of details into that, and the Google documentation has a lot of details, but just remember that the the most important way within the cluster, you have to have an IP address for each one of this service, nodes, and pods, and then you use kubeproxy for the translation of that traffic between these three. So, and that will give you a very fair idea of how the networking happens within the cluster. Now, if you step out, how does the networking happen outside the cluster? So there are primarily three options: external load balancers, internal load balancers, and HTTP load balancers. So external load balancers, they manage traffic coming from outside to the cluster, outside Google Cloud VPC network. They are forwarding rules associated with the Google Cloud network to route traffic to a Kubernetes node. Internal load balancer, they manage traffic coming from within the same VPC network. Like external load balancers, they use forwarding rules associated with the Google Cloud network to route traffic to a Kubernetes node. HTTPS load balancer. These are the specialized external load balancers used for HTTPS traffic. They use an ingress resource rather than a forwarding rule to route traffic to a Kubernetes node. Let's look at this sort of in a diagrammatic way. So, service networking is the publishing of applications in a way that abstracts the underlying ownership, implementation, or environment of the application that is being consumed by clients. So, exposing an application to clients involves three key elements of a service: front end, routing and load balancing, and back end. And that's true for any service, right? You have a front end, you need to know how to route and load balance your request, and then manage the backends. So the following example illustrates these concepts for internal and external traffic. So this is where the GCP platform is. You have an external client which uses the external load balancers to come to the application from two different locations, again through the same load balancers. And then based on where the request is coming from, and you need to connect to the backends, the traffic is routed. Now, the same goes for the internal clients. The internal clients come through the internal load balancers and they access the applications. Now, how does this, the GKE network controllers automate the creation of load balancers? Because depending upon where the request is coming from, you need a different set of load balancers. Is an infrastructure or app admin, they deploy a declarative manifest, and which is typically YAML files, uh, against the GKE cluster. And then the ingress and the service controller, they watch for GKE networking resources, such as ingress or multi-cluster ingress objects, and deploy Google Cloud load balancing, plus the IP addressing, firewall rules, and so on, based on the manifest. So depending upon what the configuration is in this manifest, that's how they deploy the applications. But the controller continues managing the load balancer and backends based on environmental and traffic change. So you collect the pod lifecycle events and then the traffic and load matrix, and based on that, it becomes a dynamic and self-sustaining load balancer with a simple and developer-oriented interface. I hope this helps you understand, how basically the networking works within the cluster, which is, there's a lot of depth into it, understanding the ingress and egress of Kubernetes cluster, and which you can refer to the documentation. But overall, it's really good to understand how the requests are routed externally as well as internally. Now, let's close this off with how the deployments are done. So Kubernetes objects can be created, updated, and deleted by storing multiple object configuration files in a directory and using kubectl applied to recursively create and update those objects as needed. A deployment provides declarative updates for pods and replica sets. You describe a desired state in a deployment, and the deployment controller changes the actual state to the desired state at a control rate. You can define deployments to create new replica sets or to remove existing deployments and adopt all their resources with new deployments. So this is how a deployment file looks like. It's a YAML file. You can either do YAML or JSON. YAML is much easier to read, so that's sort of become a de facto standard. Now, this YAML, it's what it does is it it presents the desired state to the controller, or for the deployment. Now, based on the current state, if the current state has changed or it is not equivalent to deployment desired state, that's how all of the sort of the auto deployability and auto manageability sort of kicks in, and it makes sure within the entire Kubernetes cluster that it brings the cluster back to the desired state. If you look at this YAML, and there's nothing beats the practice. More and more you practice with these deployment files, it will become easier. The first line is always the Kubernetes API version, which is used to create the object. Kind. So kind is where you provide the object type, whether it's a deployment, whether it's an application part, whether it's a proxy part, or and all of those kinds. And they're called different types of object, which in a sense is different types of configuration that you want to deploy. And then you have metadata and specs. So metadata, it's a detail to identify the object that you just described. In this particular case, it's a deployment named Nginx deployment, and you can reach to it by sort of like a dotted folder hierarchy. So dot metadata dot name will give you this value, ngx deployment. Then labels is exactly, it's an application, it's Nginx. Now specs is again, it gives the specifications for this deployment. Replicas 3. The deployment creates 3 replicated pods indicated by the .spec .replicas field. Selector. The .spec .selector field defines how the deployment finds which pods to manage, and it has a match label based on the application. Template. The pods are labeled app and Nginx using the .metadata .labels field. Then, as part of the specs, you also can provide containers, what sort of image they're going to run, what kind of ports they're going to run, what are the container pods, and all of the time, it's very important how you can navigate through it. So in this example, .spec, which is this .template, .spec, .template, .spec, .containers, 0, .name, because you can have multiple containers. So it's a very, sort of folder structure way of navigating to the field value, and which is what is used by the controller in terms of getting the value. So I hope this was useful. This was an attempt just to give you more insight into Kubernetes beyond what a certification exam requires. Kubernetes is a very hot topic. I would strongly recommend you to learn more and more about Kubernetes, because Kubernetes is becoming a de facto way of deploying applications, as long as it's concerned microservices. But with the advent of multi-cloud cluster managements and Anthos coming into picture, uh, there's a lot of investment from most organizations into Kubernetes, and not only now you can run microservices based applications, but you can also deploy monolithic applications on VMs and have a lot of different kind of applications running on Kubernetes. So it's a good topic to learn. I hope this was a good introduction and a good background, and uh, you will you'll try to learn more and more. Uh, Thanks.